everyone. So welcome back to the second video of the chapter hydrogen. So for today we are going to discuss about the various type of hydrides, the properties of water, structure of water, and the dihydrogen as fuel. Alright, so let's get started. So here as we start with the dihydrogen. Now here whenever we take into consideration of a hydrogen, hydrogen has a capacity, or you can say as hydrogen has a tendency to react with most of the elements to form binary compounds. And these particular binary compounds that have been formed after reaction with the hydrogen, we call those particular compounds as hydrides. Okay, but here one thing that we have to understand is that hydrogen has a tendency to react with almost all the elements except for the noble gases. So what happens here is hydrogen reacts with most of the elements in order to form the binary compounds, and these binary compounds we call them as the hydrides. So usually we represent these hydrides by, let's say, E represents the element, H represents the hydride. Okay, so E, H, X can be a representation, a general type of representation for the hydrides. Okay, we'll see the examples. Or sometimes we also represent these particular hydrides as En, HN. Alright, now let's take a look into the examples for these. So, in this particular case, let's say E is an element that is a magnesium. So, Mg, H2. So, therefore, here X becomes as 2 in this particular case. Similarly, B2, H6. These are called as a diborane or boron hydrides. So, in this particular case, N is 2, M is 6. So, these particular compounds which are formed, binary compounds which are formed upon the reaction with the hydrogens. So, therefore, hydrogen usually has a tendency to react with most of the elements at specific conditions in order to form the binary compounds. And those particular binary compounds, we call them as hydrides. Right? So, now, there are different types of hydrides. The first one is called as ionic hydride, or we can also call it as a salt type of hydride or saline hydride also. Second one is called as the covalent hydride. Okay, so we can call it as a covalent hydride or molecular hydrides also. Third type is called as the metallic hydrides. So, the metallic hydrides are also known as interstitial hydrides or non-stoichiometric hydrides. Right? So, therefore, we are going to take a look into the ionic hydride completely into detail, what is covalent hydride, and what is metallic or non-stoichiometric or interstitial hydrides one by one. So, coming forward with ionic hydrides. Alright, so the ionic hydrides are particularly hydrides formed when hydrogen reacts with the elements which belong to, this is very important, which belong to the S block elements. Alright, so what we can say here is hydrides or saline hydrides. These are the hydrides which are formed when hydrogen reacts with any element which belongs to the S block elements. So now, example, if I take lithium hydride, sodium hydride, right? So you can have those particular, like a potassium hydride also here. So such kind of hydrides are called as ionic hydrides. Now, why is it called as ionic hydride? That we have to understand. Here, let us say that we are choosing particularly a sodium hydride. Okay, so sodium over here is a metal. So metal has a tendency to donate electrons, right? So when it is forming the bond with hydrogen, it tends to give electron to hydrogen. So as a result of which, this hydrogen develops a huge negative charge with it. It is developing a negative charge, so therefore this is negative and this is going to be the positive. So as these hydrides generate positive and negative type of charges, we call them as ionic hydrides. Okay, so now let's say that we are taking this particular metal hydride. The important factor about the metal hydrides is that when we heat this in order to form its melt, okay, in its molten condition, what will happen is, in the molten conditions of these particular hydrides, this has a tendency to conduct electricity. Okay, so it conducts electricity only and only in its molten condition. Now, this is because when this particular metal hydride is heated, okay, the bond between these is going to be broken in such a way that this will generate H minus. So, when we are taking the electrolysis, when we are taking the two electrodes, what happens there is, under the process of electrolysis, positive terminal is called as anode, negative terminal we call it as cathode. Okay, so at the anode, this particular hydride species comes there. So this reaction occurs only at anode. So at the anode, what is going to happen is, the hydrogen with the negative charge comes over there. It loses electron, that is, the electron is transferred to this particular electrode. Once it is transferred, so therefore it loses 2 electrons. Why it is losing 2 electrons? Every single hydrogen with a negative charge is giving 1 electron, and that is going to be escaping from the anode in the form of hydrogen gas. Okay, so by this particular experiment, it reveals, it proves that the metal hydrides over here are going to conduct electricity in their molten condition, right? So, going forward with one more important aspect, taking a look into one important aspect here is about the lithium hydride. Now, this lithium hydride is unreactive. It is not going to react. It is unreactive with oxygen and chlorine at the room temperatures only. We are speaking strictly with respect to room temperature here. So as a result, what is happening is that the lithium hydride is not going to react with oxygen, neither it is going to react with chlorine at the room temperature. With the help of this, we can create, we can synthesize, we can produce new and different types of hydrides. Okay, so therefore, because of this particular property, lithium hydride is used in the synthesis of different hydrides Okay, so what are the different hydrides? We are going to take a look into the example. So example over here as what we have is when lithium hydride reacts with Al2Cl6. Okay, of course it is not balanced. So therefore, when aluminum reacts, we are going to get lithium aluminium hydrate. Okay, so plus what is going to happen is, as we have 2 over here, let us take over here as 2. Okay, so if I take it over here as 2 into 4, that is 8. That means there should be 8 lithium hydride in order to balance them. So we have 8 hydrogens over here. 2 into 4 is 8 hydrogens, perfectly balanced. 2 lithiums, but we have 8 lithiums here. That means out of 8 lithiums, I am using 2 lithium over here. Remaining are 6 lithium. So therefore, 6 lithium. Okay, and we have 6 chlorines, so this should balance it. Okay, so this is a way as how lithium hydride has been used in order to synthesize different types of hydrides. Another example, lithium hydride reacts with B2H6, that is diborane, in order to get lithium borohydride. Okay, so let's check. So 2 borons over here. 2 into 4 is 8, but here we have 6 plus 1, 7, so we will take over here 2. So 2 lithiums, 2 hydrogens plus 6 hydrogens, that becomes as 8 hydrogens totally at the reactive side. So 2 into 4, again, that what we have is 8 hydrogens on the product side. So these are called as a balanced chemical equations. Now here we have created lithium borohydride. Here we call this one over here as lithium aluminium hydrate. So this is how it follows. Now one more important thing that we have to discuss here is that whenever we see the ionic hydride, what we had considered is that the bond between the element and hydrogen. This bond we had considered it to be as an ionic, okay, due to which it was generating charges. Now, it is not true for all the elements of the S block. When we take a look into the lighter elements, okay, so when we take a look into the lighter elements, what lighter elements I am speaking here is about, such as lithium hydride, magnesium hydride, beryllium hydride. Okay, in such cases, significant amount of covalent bond is also been observed between the two atoms. So in such cases, whenever we are taking a look into the lighter elements, in these particular elements, there is significant amount of covalent bond that has been observed. Alright, so this is the important point for us. Right? So now we shall take a look into the next section, and that is going to be the molecular hydrides. So coming forward with the next one, and that is going to be the molecular hydrides. Now here, in the molecular hydrides, when we are speaking about the molecule, first thing that we have to understand is that in such kind of species, between the two atoms, there is a covalent bond that exists. In the previous case, there was an ionic bond, and here predominantly it is going to be the covalent bond. Now, covalent bond is a bond that is formed due to the sharing of electron. Okay, both the electrons are going to be shared between the two different atoms. Correct? So, in such cases, whatever the hydrides that we are going to get, we call them as the molecular hydrides. So, in the molecular hydrides, when we take a look, what occurs over here is that when hydrogen reacts with the elements of P block. So, important thing now here is that the P block elements, when they react with the hydrogen, they form molecular hydrides. Okay, so therefore it leads into the formation of the hydrides, which are called as the molecular hydrides, or we can also call them as the covalent hydrides. Now, whether it is a molecular hydride or covalent hydride, these particular hydrides are again further classified into three varieties. Depending upon, it all depends upon how many number of electrons they are present. Okay, so depending upon the electrons which are present between the two, that is between the hydrogen and the particular element. Okay, between these two, how many number of electrons are there, whether the electrons are safe and sufficient, whether the electrons are precisely what are required, or whether the electrons are deficient. Depending upon that, we are going to classify it into three categories. The first category is known as the electron deficient hydrides. Alright, so these are the electron deficient hydrides. That means between the two elements, the number of electrons are less. Okay, when we represent its Lewis structure, we cannot have sufficient number of electrons. Okay, we are going to discuss in detail about this. So, second one is called as the electron precise hydrides. While the third one is called as the electron rich hydrides. Right? So, we have the three conditions, that is the electron deficient hydrides, electron precise hydrides, and electron rich hydrides. We are going to take a look into each one of them now. Okay. Now, coming forward with the electron deficient hydrides. So, in the electron deficient hydrides, what happens here is that whenever there are the hydrides in which the number of electrons are less, in order to represent the Lewis structures Okay, so that means that whenever we are trying to represent a Lewis structure for a given hydrides, we fall short of electrons. We are unable to represent that particular structure efficiently because the number of electrons are less. For example, we will take over here example, that is B2 H6. So in B2H6, what usually happens is 1, 2, 3. Okay. So a boron over here can form 3 bonds effectively. Okay. But the 4th bond is going to be formed sometime over here like this. But the same hydrogen forms a perfect bond with the next boron, and this particular boron is again going to be shared between the two. So here it becomes difficult for us in order to represent a Levi's structure, because number of electrons that have to be shared are less. Now in this case, actually for a boron hydride, what happens is these hydrogens are small and they cannot donate their electrons. So only the half section, that is BH3, cannot be stabilized. It is not going to be stable. It cannot be formed. In order to become stable, it dimerizes itself. Dimerizes means it connects with another one only in order for its stability. To increase its stability, it is going to dimerize. So there is where we get B2H6. Okay, we cannot just get as BH3 as a single unit in this case. Alright, so going forward with the next one, and that is called as the electron precise hydrides. Now, these are particularly the hydrides wherein the number of electrons are exactly what are required for us to represent a Levi's structure. For example, let us say that we have CH4, a simple methane, right? So when we speak about this carbon in this particular case, so carbon in its excited state has 4 valence electrons. Okay, that means we are going to use this particular 4 electrons. So a Levi's structure is drawn something like this. This is a carbon and we just represent valence electrons. So how many valence electrons do we have? 1, 2, 3, 4. So how many valence electrons do we have? Here is 4, right? Now these 4 electrons are going to be shared something like this, right? So this is a Levi's structure for methane. So here the number of electrons which is required are exactly equal to that what we can draw it in its Levi's structure. So due to the sharing of these 2 electrons, a bond is formed. Because of sharing of these 2 electrons, another bond is formed. Due to the sharing of these 2 electrons, another bond is formed. And finally, the same occurs over here. Okay, so this is the Levi's structure for the methane in this case, right? So coming forward with the next one, and that is going to be the electron-rich hydrides. So electron-rich hydrides, that means in this particular case, the element is going to have excess number of electrons than what is required for us in order to represent the Levi's structure. Let us take some example. So here, if I take an example of H2O water. Okay, so here, oxygen forms a center element or an atom with 2 hydrogens. And here, this oxygen has 2 lone pair of electrons. So the number of lone pair of electrons are 2 in this particular case. Similar is the case if I am going to take over here ammonia. When we take ammonia into consideration, nitrogen has 1 lone pair of electrons, 1, 2, 3 bonds to the hydrogen. If I am going to take into consideration of HF, Okay, so here there is one lone pair of electron, that is an extra electron in this particular case. Okay, of course, we can represent this entire scenario as a Levi structure by putting two dots over here. Not a problem. Now, when we take a look into HF, what will happen? Hydrogen fluoride. So, in this case, there are three lone pair of electrons. So, 1, 2, 3. So, there are three lone pair of electron in the case of HF. So here the number of electrons are great, or you can say as the number of electrons are more than what is required in order to represent their Levi's structure. So this is the case of the molecular hydrides, or what we can call it as the covalent hydrides. So coming to the next section, and that is going to be the metallic hydrides. We also call them as interstitial hydrides, or we call them as the non-stoichiometric hydrides. Okay, so we have the two in this particular case. So this particular case is formed when a hydrogen reacts. Now it reacts over here with the elements, of the D and F block. Okay, so in this particular case, whatever the compound that is formed, that is called as the metallic hydride, right? So here, these particular metallic hydrides have one important property, and that is it can conduct heat and electricity. Right? So it can conduct heat and electricity, but it is not so efficient, it is not so powerful as their parent element would. Okay, so therefore, but not as efficient as the parent elements. So this is the important thing what we have to keep in our mind, that is, it can conduct heat and electricity, but these hydrides are not that efficient in conducting the heat and electricity as that parent element would do. Okay, now coming towards the next important point over here to discuss is that these are called as the non-stoichiometric hydrides. Non-stoichiometric hydrides. First, let us observe the particular examples and then we can discuss over here. Okay, so this is the lanthanum hydride, wherein the proportion between the hydrogen and lanthanum metal is not constant. Rather, it is 2.85. It's not a perfect whole figure in this case. Okay, as what we used to write it for magnesium hydride. So here there is one magnesium and there are two hydrogens. But here that ratio is not fixed. Okay, so in such kind of condition, your law of constant proportion absolutely fails here. Okay, we cannot apply that rule in this particular scenario. So second one, as what we can have is going to be yttrium hydride. In this particular case, it is going to be 2.55. So the third example, as what we can take is titanium hydride. In this scenario, the proportion of hydrogen is again not fixed. It varies, at least in this particular case, and that is from 1.5 to 1.8. Alright, so in this entire case, what happens is that we cannot use the law of constant proportions. Okay, so now coming towards the next application point of view of the metallic hydrides. So when we take a look into the application point of view, here these metals, let's say that these are the metal surface, and in this particular metal surface have a particular tendency. The tendency is that they can adsorb the hydrogen gas on the surface. Now I am speaking here as adsorb. I am not saying absorb. Adsorb means the gases are held on the surface of these metals. So these are, let's say, the hydrogen atoms. And this is, of course, the surface of the metal what we are taking a look into. Okay, so now when we take a metal which has a property of adsorption and which adsorbs hydrogen effectively, these kind of metals are taken for the applications such as selective reductions. Okay, so therefore it is taken for selective reductions, or you can also call it as the catalytic reductions. Okay, so it is taken into consideration for the catalytic reduction or selective reduction. So this particular phenomenon is called as a process of adsorption. Coming towards the next phenomena, and that is called as the dihydrogen as fuels. So here usually the hydrogen gas is used in the fuel cells. Okay, now it is used in the fuel cells because whenever we take hydrogen and we burn it, we supply in the energy. Now this particular hydrogen burns, emitting a large amount of heat, due to which this hydrogen is preferred for the fuel cells. Now, when we burn it into the fuel cell, there is a very less amount of pollution, and the pollution which we get over here is a very simple oxide of nitrogen. Now again, this particular thing can be sorted out because as the hydrogen is going to be burning at a bit of higher temperature. Okay, and in this scenario, in this case, if we insert, okay, if we are going to insert small amount of water here, small amount of water into the fuel cell. So that particular water, what it does is it cools down the temperature and it will not allow the reaction between this particular water, will not allow the reaction between nitrogen and oxygen due to the lower temperature. Okay, this is due to the lower temperature. So therefore, again the pollution can be reduced. So therefore, it has been advised to use the fuel cells. So in the near future, you can expect the fuel cells in use at the larger scale. So what happens in fuel cells is that in the fuel cells, we take hydrogen we try to compass that hydrogen because it emits a large amount of heat energy. Now during this particular process, of course there are some amount of pollution, that pollution being oxide of nitrogen. And this particular oxide of nitrogen can be reduced by inserting small amount of water into the fuel cells. Now this particular water, what it does is that it lowers down the temperature and it will not allow the nitrogen to react with oxygen. Right? So this is how they are going to minimize the pollution. Okay, so getting over to the next section, and that is going to be the study of water. Now, when we are speaking about water, before going to its structure, let's speak about its simple elementary facts. So first thing that what we know is all the living organisms are made up of water, right? An adult human being or a human body consists of 60 to 65% of water. There are few plants in which the plant body is made up of 95% of water, right? So finally, as what we know, the scientific representation, chemical formula is H2O. So now, when we speak about an H2O, here, when we are taking a look into the structure of water, let us speak the structure with respect to the gaseous phase. So in the gaseous phase, when we take a look into this particular water molecule. Now here in the water molecule, the most important significant thing is the oxygen. Okay, now this oxygen, what is present in the water molecule, it is an sp3 hybridized. What is meaning of sp3 hybridized is that it has an s orbital. Let's say it has an s orbital. This s orbital combines with px. It combines with ty, and of course it also combines with pz. Once it combines, it is going to have 4 lobes because 1, 2, 3, 4. 4 atomic orbitals are getting combined in this particular case. As a result of which, there are going to be 4 lobes to the oxygen, something like this. Let us say that this is your oxygen. Okay, so now in this particular oxygen, what will happen is there are 2 lobes over here like this. Now these 2 lobes are going to help us for the formation of the bond with hydrogen. And hydrogen of course has just one orbital, that is going to be 1s. So therefore, this is how the overlapping between 1s orbital and sp3 hybridized orbital of oxygen occurs. You are going to study this into detail in the chapter which is called as the chemical bonding, one of the most important chapters in chemistry. Okay, so now here there is one hydrogen and here there is another hydrogen. Okay, so this is how the hydrogen forms the bond. Now remaining are these 2 lobes. Now these 2 lobes are situated over here like this. Okay, with 2 electrons here and 2 electrons over here. Now in this case, what will happen is between these 2 lobes, because of the repulsion between the 2 lone pair of electrons, Okay, these are called as the lone pair of electrons. Okay, due to this, there is a significant effect on the bond between the oxygen and hydrogen. Therefore, the bond angle here reduces up to 104.5 degrees. Okay, now taking a look into what is the length from oxygen to hydrogen. If we do represent this as oxygen, lone pair of electrons, hydrogen here, okay, and of course what we know is this particular angle is 104.5 degrees. Now, this particular case, that is the length between the oxygen and hydrogen. Now, this length is going to be 97. Is going to be 95.7 picometers. Okay, and the entire shape, this is important, the shape of this water molecule is going to be a bent shape here. Okay, that is going to be the bent shape. So, in order to visualize that, we'll take the help of a model. So, taking into consideration of a model, if we observe, let's consider the red color sphere is the particular one which is the oxygen. Okay, and the one with the lavender, let's say that is a hydrogen. So here, there is one bond to the hydrogen here, another bond to the hydrogen. The bond angle here is going to be 104.5 degree. The bond length is going to be 95.7 picometers. While if we do observe these two are representing to us a lone pair of electrons. So this particular structure is called as the bent structure. Right? So now going further. Okay. So looking further into the details of the structure. First here, what we know about the water molecule is that this particular shape of water molecule is going to be bent shape. Right? Due to the bent shape, what happens here is, due to this particular geometry, it has an effect on its net dipole moment. So, the net dipole moment of water molecule is going to be as 1.84 d bar. So, this is the dipole moment. Right? Now, coming further. So, when we take a look into the water with respect to its two states, one is a liquid state and the another one is a solid state. So, in this particular scenario, what happens is, in the liquid as well as in the solid state, there occurs to be an interaction between the molecules, and this particular interaction between the molecule is because of the hydrogen bonding. So, now hydrogen bond. First, let's speak about the solid form of water, and that is nothing more than the ice. So, when we have here when we take a look into a solid form, what happens is the particular water molecule are being affected by the hydrogen bond, due to which it creates a vacant space in middle. Due to this particular vacant space, the density of that particular solid, that is the density of ice, decreases. But as we heat this particular solid ice, as if the particular solid ice melts, As it starts melting, the hydrogen bond goes on detaching. It has a direct influence on the hydrogen bond, due to which the vacant spaces disappear, because the water molecules are going to be densely packed. Okay, due to which the water has higher density when we compare to that of ice. Usually the density of water is quite very high at 4 degrees Celsius. So this is it for today. We'll meet you in the next video. Thank you and have a great day.